Hi everyone. Today we'll be conducting the motherboard training session. So today we'll be going over system design, MIPS assembly, and then SPI, SPI.
Sure. Okay. So wanted to start off by asking the question, what is system design? And basically, it's the process of defining architecture, modules, interfaces, and data for a system to satisfy specified requirements. And that's basically what 127 was, right? So in 127, you design peripheral blocks, and then you design interfaces between the microprocessor and the peripheral blocks, and then you wrote code for the microprocessor to drive the peripheral blocks through these interfaces. Okay. So now we're going to do a demonstration of the motherboard I/O project. So I'm going to start.
This is a simple project on just using the onboard switches and LEDs. So,
Okay, starting the video now. Ooh. There we go. Click the play button. There we go.
So in the RAM are loaded some values, and the CPU will go ahead and read from the RAM and go ahead and light up the corresponding LEDs. Then it's up to the user to match the corresponding LEDs. And then when they do match, the CPU will go ahead and then turn off the LEDs. And then when the user goes ahead and turns off all the the switches again, the program will restart. So the switches and LEDs are memory mapped, and we'll be discussing how this was constructed.
Okay. And the link to the project is also listed on.
Yeah, so this is currently posted on my GitHub. You can go ahead and download it, clone it, and then test it out on your own FPGA boards. So putting it all together, we have the MIPS processor. So this is your CPU. You have an address and data bus. The data bus is bidirectional, so you can both input and output. Then you have your control signals for external devices. You have the read signal, and you have a 4-bit write signal. This is all documented in the drive. The write signal has 4 bits to basically tell you whether it's going to be a word, which is 32 bits, half word, which is 16, or byte. You have the program counter, which drives your program, so go ahead and increment and fetch each instruction. And that instruction is then fed into the instruction port. So your assembly instructions, which are going to be encoded in hex, reside in the ROM, which is read-only. The program counter will go ahead and increment each address as your program runs and output that instruction to the CPU. And then you have your RAM, which is your external memory. So for this RAM, it's configurable. In the module, you can go ahead and choose the size of your RAM, the data width, and based on those, it'll automatically calculate the number of bits for the addresses. So in my example, I use 4096 kilobyte RAM with a 32-bit data width, just so it's easier to interface with a 32-bit data bus. And as such, we calculated a 10-bit address line. The data here is also bidirectional, so both reading and writing is done through the same port. You also have a 4-bit write enable, which directly gets connected to the MIPS processor. And you have an output enable, which is essentially the read signal. And this is the basic connection. So you have the MIPS processor. It gets connected to the RAM. You have the bidirectional data bus, the address. So in this case, we don't use the lower 2 bits to make the reading of the RAM word aligned. And as previously discussed, the program counter is the address for the ROM, and the instruction gets outputted to the MIPS processor. Any questions as of now? Yes?
Why is the write enable 4 bits?
Yeah, so that's to determine whether you're reading word, half word, or byte. Any other questions? Should we check in the chat?
No questions in the chat.
Does anyone in the chat have a question? I've turned on the volume so I can hear you. Okay, moving on then. Okay. So for the input, we're using a tri-state buffer with an output enable. So the switches are an input, and you're able to assert a read signal to basically output enable to allow that result to show up on the data bus to be read. And then you just instantiate this module and then connect it through the constraint file, so through the XTC. And then likewise for the LEDs, we have a register, which is based on the clock as well. You have a write enable for this, and then it's also connected to the data bus. The data bus is actually bidirectional. I did not indicate that. And then the output of this register just gets directly connected to the LEDs through the constraints. And then for my implementation, I decided to go with this memory map where we have RAM starting at address 0. However, it's up to you to configure it however you want, as long as you implement the corresponding address decoding. My output and input devices are also memory mapped, so I also decided to pack them sequentially, so they're all following one another. But again, that's up to you to decide how you want to configure that. So to accomplish that, this is the logic that I came up with. So when deciding between address and memory, I did full address decoding. So I ensured that all upper bits that were not used for the actual address were 0 through this equation. And then I used the 12th bit to decide between address and memory, like you've discussed in 127. And then I used the lower bits to putting it through a 2 to 4 decoder to basically control whether or not I wanted to select my input or output devices. So here's a block diagram of how that looks. So the upper bits are going through a NAND gate, and then further decoding occurs. However, you need to also incorporate the read and write signals. So this is it expanded. For my purposes, I didn't care about the 4-bit write enable, so I went ahead and put it through an AND gate to give me a 1-bit signal to tell me whether or not all bits of the write enable were asserted or not. So, as discussed, you have the tri-state buffer controlled by each individual address decoded signals. Any questions? Any questions in the video call right now? Yeah, so this is it all put together. It's kind of small. So as discussed, for the motherboard project, we have a clock generator, which basically reduces the speed of the onboard clock, and that's fed to the MIPS processor. You can also configure that to whatever speed you want, but if you're using SPI, there's a certain speed that you want SPI to be at, and therefore MIPS will also have to be at a corresponding speed. We'll discuss that in a later time. So also link this for you guys to see, just so you can understand how everything is connected. Yeah. Yeah. Okay, and that's it for our system design. Does anyone have any questions? Okay.